Hello, in this video we are going to study about virtual memory and memory management hardware. So what is virtual memory? Virtual memory is a concept used in some large computer systems that permit the user to construct programs as though a large memory space were available. Virtual memory is used to give a programmer the illusion that they have a very large memory at their disposal, even though the computer actually has a relatively small main memory. So there are these four addresses that you need to know before moving ahead. What is virtual address? Virtual address is the address used by the programmer. Address space is the set of all the virtual addresses. What is location or physical address? It means the address in the main memory, and the memory space means all physical addresses, the set of all the physical addresses. Okay, so once you are clear about these terms, take a look at it, then only move ahead. Okay, so let's see how it works. Let's say that we have a virtual address of 0, 4K, 8K, 12K, 16K. So these are the virtual addresses having the values of A, B, C, D, E. So this is how we do our programming. But on the back end, the main memory and my secondary memory, the hard disk. So at those places my different values have been saved. You can see clearly at memory location 0 in the virtual address it is A, but it is available at 24K location of the physical address in the main memory. Similarly, B is at the 4K address of virtual address, but it is available at 16K address of the physical address. Similarly, D and E are in the secondary memory. Secondary memory means that the hard disk or something like that. Okay, the secondary memory came late initially when the systems were designed. Even in case of 8085, 8086, when you study microprocessor, in that also when we say address, it is by default physical address, because at that time in 1970s 80s there was no secondary memory, it was only the physical address, it was only the physical memory. Okay, yeah, let's continue. Now, what is address mapping using pages? Address mapping is simplified if the address and memory space are each divided into groups of fixed sizes. So the physical memory is divided into fixed size blocks, or called as page frames. Address space is divided into fixed size pages. So my physical memory is divided into blocks. Address memory, the address space is divided into the pages. So the pages are in the virtual memory and blocks are in the physical memory. Now consider this. Consider a computer with an address space of 8K words and a memory space of 4K. If we split each of these into the groups of 1000 words each, we will obtain 8 pages and 4 blocks. So 8 pages in the virtual memory and the 4 blocks in the main memory. Address space means virtual memory and memory space means the main memory. At any given point of time, up to 4 pages can reside into the main memory in any of the 4 blocks, obviously, right? We have only 4 blocks here. Let's move ahead. What is address mapping? So we have to convert our virtual address into the main memory address. We have to fetch it and get the work done through the main memory. So this is the way to do it. Initially, my virtual address, when we have this virtual address, we have to check the virtual address register for the memory mapping table. And when we reach the memory mapping table, we get the value of memory table buffer register. Then moving ahead, we get the main memory address register through the physical address. Okay, and then the main memory, and you will see an example later on. Okay, let's go ahead. So in this example, obviously see the top, there is a virtual address 101.01.01.01.0011. So in this, the first 3 bits are the page number and the other bits are the line number. So using the page number you can assess this memory page table. This is the table address. This 101 means the location 01. Okay, so the 01 is passed on to this one. 1 means the presence bit, so this one means the presence bit. 1 means page is available in the main memory. Okay, so yeah, okay, then this 01 is passed on, the line number is copied here, and we can shift this main memory address register all of the data into the block 1, and finally it is sent to the MBR, which is memory buffer register. Okay, let's go ahead. So what is virtual memory associative memory page table? Okay, so consider this example. A random access memory page table is inefficient. Why? So consider an address space of 1024K words and a memory space of 32K words for page or block size of 1K words. So the number of pages are 1024, the number of blocks are 32. Okay, Capacity of the memory page table is 1024 words, but only 32 locations will be occupied. This means in the form of this k, okay, 1024k and 32k. So we are wasting a lot of memory in this. A memory efficient way should be constructed so that the page table with the number of words should be equal to the number of blocks in the main memory. So there should not be wastage of memory. Okay, so this associative memory page table is how we try to handle that problem. So page number bits in the argument register. So this is the argument register having the page number and the line number. Page number bits in the argument register are compared with the all page numbers in the page field of the associative memory. Okay, so this is my associative memory. It is compared, the whole value is compared with this one. If the page number is found, the corresponding word is read from memory, otherwise the required page is fetched from the auxiliary memory. So this memory means the main memory, auxiliary memory means the virtual memory, and if it is being fetched from the auxiliary memory, it is sent to the main memory. Okay, consider this as an example. Let's say that we don't have anything, we don't have the value which we want in the main memory, so we have to fetch it from the virtual memory or the auxiliary memory. Okay, so this is how it's done. I mean, I hope that you understand this figure. It is very easy to understand. So 101 and the line number, the key register is this one. So at 101 location we have this 01, and obviously this part it will be sent to the main memory. So what is virtual memory page fault? When a program starts executing, one or more pages are transferred into the main memory and the page table is set to indicate their position. Okay, the program is executed from main memory until it attempts to reference a page that is still in the auxiliary memory. Okay, so the thing is that when the program is being run in the main memory and we are fetching the values and the variables out of the main memory, sometimes it can happen that we don't have the actual value we want in the main memory, so we have to fetch it from the auxiliary memory. When there is a miss, we call it a page fault. When there is a miss in the main memory, it is called a page fault. Okay, when page fault occurs, the execution of the program is suspended until the page required is brought into the main memory. I hope it is clear. It is very easy thing. Let's move ahead. So let's say that we wanted to load this m memory location, so it will be checked in the page table, and based on this, trap signal will be sent to the OS, and OS will send a request to to check in the backstore. It means the main memory, it means the secondary memory. So the backstore means it is going to scan the secondary memory. So from that it will be bringing the missing page into the free frame of the physical memory, and it will be sent to the page table. The memory will be loaded. So these are the all 6 instructions that need to be done for when there is a page fault. Let's move ahead. What is page replacement? So if there is a page fault, obviously now if there is a miss, if the value is missing, obviously it has to be replaced. Okay, so considering that, let's read this. If a page fault occurs and there is no free space in the main memory to accommodate the required page, let's say that my main memory slot is full. Let's say that there are 3 slots in the main memory which we consider as a word. Generally it is more than that, but let's say there are 3 locations which we consider as a word, and we don't find the actual value in that location, so we have to replace. If it is full, we have to replace the previously available values in the main memory. So there are multiple techniques to do it. There are 3 actually. The first 2 are this, FIFO and LRU. FIFO is first in first out, LRU is least recently used. Okay, let's see the detail. The first in first out is replace the page that has been in memory the longest. Obviously it is easy to implement but may result in frequent page faults. Okay, so it is understandable also. The one which is in the queue, which is in the memory the longest, it should be removed and someone new should be brought in. Okay, so what is LRU, least recently used? Replace the page that has not been used for the longest period of time. Okay, now least recently used means that if some value has not been used for a long period of time, it means it's not been fetched or may not be used in the program, so it can be replaced because it is useless anyway. So relatively it is more difficult to implement but reduces the page fault rate. Okay, so the page fault and the missing rate will decrease, but it is relatively more difficult to implement. The other one is the optimal page replacement algorithm. So there is a typo here. Okay, LRU is technically an alternative for the best page replacement algorithm. Generally what happens is, there is one more algorithm which you must have studied in the operating system also. Optimal page replacement algorithm means that replace those values which are not coming soon. Let's say that we have a page. Let's say we have these four slots in the pay replacement. So what we need to do is, we need to put the values here such that, let's say we have a queue of 1 2. Let's consider these numbers. Let's say that we need to fetch these one by one and fill in these four locations. So when we fetch the 2 initially, there is one pay fault because it is not available initially. Again 2, it is available, so it's okay. The third one is 1. 1 should be put here. Then 0, it should be put here. Then 5, it should be put here. Then again 0. So 0 is there already, it's okay. We don't need to replace anyone right now. So 1 1 2, I mean they're all available. Now when the 3 comes, we need to see which one out of these 4 is to be used, the is not required right now and will be called very late in the queue. So obviously we need to know the queue in advance, and we will see that 5 is the one which is to be used very late, so we can replace the 5. So this 3 will technically replace this 5 location, and it will be replaced as 3. Okay, so this is how optimal pay replacement algorithm. So this is also one of the drawback here, because we need to know in advance that what is the full queue. Then only we can compare these 4 values with this one and check if this 5 is coming very late or it is coming soon. So this is the drawback. Okay, and it is not I mean it is impossible to implement in practice, because we do not know actually, when we are running a program, we do not know that which value will come and which will not come. Okay. Okay, moving ahead. So now, memory management hardware. A memory management system is a collection of hardware and software procedures for managing the various programs residing in memory. Basic components of the memory management unit is the facility for dynamic storage relocation that map logical memory references into the physical memory addresses. Obviously we need to map these two. Provision for sharing the common programs stored in memory by different users. Protection of the information against, obviously then the security also comes in. Okay, so these are the three things which are the basic components of the memory management unit. And this dynamic storage relocation means that it is a mapping process similar to the paging system discussed earlier. Okay, the fixed size pages used in the virtual memory system causes certain difficulties with respect to the program size and the logical structure. You will see later on what all these things mean, but this is the main thing here. So it is much more convenient to divide programs and data into variable sized logical parts called segments. So these segments will come into the picture now. Let's see what they are. So these are the segments. This is subroutine segment, this is stack segment, this is system table segment, this is main program segment. Okay, so all these are part of their logical address. So users prefer to view the memory as a collection of variable sized segments. It means that it can have different size than this one. Okay, this can have a different size than this one, and with no necessary ordering among segments. The segments need not have any particular order. Okay, so a segment is a set of logically related instructions or data elements associated with a given name. Examples of segments are a subroutine, table of symbols, or a program. So these are the segments. I hope you understand the idea behind this. Then what is segmentation versus the virtual memory? The address generated by a segmented program is called a logical address. So okay, this is similar to virtual address, except the logical address space is composed of variable length segments rather than fixed size pages. So what was happening in the virtual memory, there was fixed size pages, and in this we have variable length segments. So this is a very good difference that we can save on memory. If we need a less size of segment, we can have that. We need not waste the rest of the page which is not being occupied. So the logical address space may be larger than the physical address space, but it can also be equal or sometimes even smaller than the physical address space. Yeah, it depends on our use case, so the size can vary. So these are the segmentation mapping using the segment table. So what we need to do is, this is my segment, these are my segments in the logical address space. So this is my segment table. What we need to do is we have to map it in the physical memory. But how it is done? So the base value 1400 is picked, and limit means 1000, so we have to move 1000 locations starting from 1400. So 1400 to 2400 is my segment 0, 6300 to 6700 is my segment 1, 4300 to 4700 is my segment 2. This is the one here. 3200 to 4300 is my segment 3, this one, and 4700 to 5700 is my segment 4, this one. Okay, so this is how we map it. We have to use these two values, limit and base, to generate this segment table, and based on it we can map it in the physical memory. Let's go ahead. This is how the sharing of segments happen. I mean, obviously this is how this logical memory process P1 and P2, there can be multiple processes, right? So in process P1, there are some values of base and limit. Obviously you can add these to 43,062 to adding this number, and we reach this 68,348. So this segment 0 is the editor. Okay, so this editor is written here, that's why it is editor here. So because segment 0 is editor, so you can map these two with this one and check this, verify this physical memory. It is very easy. Okay, moving ahead. So segmented page mapping. How do we map logical address with physical addresses? Well, there are two methods: logical to physical address mapping and the use of translation local site buffer, TLB. Okay, let's see how it works. So we can use this logical address. We have to pick the segment value and map it in the segment table. The value to be picked here should be added with the page value. These two adding will give us the page table location, and using that value can be fetched into the block, and this word can be appended with it. So this block and word will make up for the physical address. Moving ahead, let's see an example. So yeah, it is the same thing is written here. So the values need to be processed like the one I have explained already. There will be example. There is example coming in the next slides. Okay, so implementation of page table and segment table. The two mapping tables can be stored into separate small memories or in main memory. Either way, memory reference from the CPU will require the three accesses to memory, and one from the segment table, one from the page table, and one from the main memory. So these three are responsible. But now the speed becomes slow because we have these three things to be done, and alternative is using a fast associative memory to hold the most recently referenced table entries. Okay, let's see. So now the translation local site buffer. The fast associative memory used to hold the most recently referenced table entries in some is sometimes called translation local site buffer. So what the fast associative memory does is it keeps the record of the recently used values, and it keeps the record of the segment, page, and block. So we will see an example now how it works. So this is how it works. You can check this. You can map with this one. I told you that the example is coming. So use this table, use this figure to solve this one. So what you have to do is you have to take the 6 value, this is 6 here, so you have to take the 6 value and go to this location. There is 35, you have to add this 35 with this 2. 35 and 2 is 37, which is this one, so you get the value 019. You have to append the value here of the word. So this 7e will be appended with this one, so 0197e is the address here. So these are the 32-bit word. This is the 32-bit word which you need to assess, 0197e. So this is how you map it. Okay, logical to physical. Moving ahead, so if we go to 6 plus 4, 39, so 35 plus 4 is 39. So A61 and 7e, A61 7e means that obviously A61 is my block here now, and it can be appended with the this word. Okay, so A617E is not in here because I mean, this is an example of how we maintain that TLB table. So this is how we maintain the TLB table 604 A61. I mean, depending upon which value you need to check, which value you need to reach in the physical memory. Moving ahead, so this is how we do the memory protection. We have I mean, memory protection through the physical address also and the logical address also, and each block in the memory is assigned a number of protection bits that indicate the type of access allowed to a corresponding block. Okay, so every time a page is moved from one block to another, protection bits need to be updated. So now if something is there in through the physical address, obviously when there is a movement of the bits, so the protection bits also need to be updated. Okay, whichever place it reaches, there should be updation of the protection bits also. Similarly, in the through the logical address, the protection information is included within the segment table or the segment register of the main memory hardware. Let's see what it means. So there are three things which needs to be checked. The content of each entry in a segment table or segment register is called a descriptor. So this is my descriptor. It has three things: the base address, the length, and the protection. So the base address is used for mapping logical to physical. Okay, the length gives the segment size by specifying the maximum number of pages assigned to a segment. Okay, the size violation occurs if the page number falls outside the segment length boundary, understandable. And then the protection, so it specifies the access rights available to a particular segment. So there are multiple types of accesses. So these are the full read and write privilege, read only, write protection, execute only, program protection, and the system only means OS protection. So these are the access rights that are used for protecting the programs residing in the memory. Okay, yeah, thank you.